Hi, I'm Carl, and in this video we're going to go over questions 90 to 93 of section 3 of the pink booklet. So this is a question about genetics, and we're given quite a lot of information to answer this question. I want to draw your attention though to the bottom of page 82. So this has a sentence here after this table showing all the different combinations of base pairs you can get when you have two bases, and it says that not all of the two base pair sequences in the table are different. A simple rotation shows that, for example, the following sequences are identical. And so it gives that example, and that's really important for this question, so make sure you've read over it properly. And we'll start with question 90. And it says, consider the single strand sequence that I've copied out here. Which of the following sequences would base pair with it? Okay, so I've written out the base pairing rules, which I'm sure you already know. The only other thing that might be new is having these numbers, these 3' and 5' ends. So for every 5' you need a 3', and vice versa. Okay, so now we know these rows, let's fill in the blanks and work out what bases would fill in these gaps. So let's see, we've got G, T, A, T, A, G. So looking at the answers, that's not actually one of them, but we've been told about these identical sequences. So what if we flip this around, if we did like the mirror image of it? So starting here, let's put 5', and then G, then A, and then T, A, oh, T, A, T, C, 3'. So that's going to be the mirror image of it, just writing it that way. If we have a look at the answers, then we can see, and that's going to be answer A. So that would bind with it, because they're identical, they're the same thing, it's just flipped around. Okay, so 91 then says, which one of the following represents identical double-stranded sequences? So at the start, this seems like a bit of an intimidating question, because there's quite a lot of detail. But there's actually some really quick ways that you can work out whether or not any of these options are viable. And of course, with this sort of question, you just have to go through them. So we'll start off with A. And we can actually work out what its identical version would be. So let's just start with this top sequence here. So if we were to write this backwards, that's what it would be in its identical form. So we get 3', A, C, 5'. And we can see that that's not present on this side, so we can rule A out. Again, looking at this top one, we can write it out backwards. So we'll go 5', T, C, 3', and it's not present here, so we can rule out B. Again, just looking at this top one, we can write it out backwards. 5', A, T, 3'. And we've got something close here, but it's not quite there, so it's a no. And then what about D? So again, we'll take this one. We want 5', A, G, 3', which we can see here. Great. So just to check it, we'll check another one. Of course, if one half of this is correct, and the one has to be because they're mirror images of each other. But we'll just check this next one. So we'll want 3' up here, T, C, 5', which is what we've got. So the answer for this one is going to be D. Question 92, then, before we move on, it says how many different double-stranded sequences containing only A and T are given in the table. So I haven't copied out the table because there's an easier way of doing this. If you've got sort of these two options, A, T, or both, then you've only got so many combinations. So obviously the first one you've got AA, then TT, and then AT. So you might think, oh, well, what about TA? But because these are identical, you'd consider them actually to be the same one. And that's all the possible combinations of those two things. So there's only going to be 3 in the table. And that gives us an answer of C for 92. And then 93, we've got this 16 residue single-stranded DNA. And we're told that it can bind to itself, or other single-stranded molecules could come and bind to it if they were complementary. So in a solution where you've only got strands of this oligonucleotide, what's the longest double-stranded molecule that can form? So I think actually visualizing this could help. So say you've got this single-stranded line of DNA, and you've got another one that comes up to it. If there's some complementary bases, they'll pair up like this. And so you get a region here that is double-stranded, or DNA. Or ddNA double-stranded. And so what do you do with this? If we're told what's the longest double-stranded molecule, well, if we're going to maximize this region, you've both got two strands that are both 16 residues long. What if you slid this one this way and this one this way, so it looked like this? So you had 16 residues all here, and then you had this region of ddNA that is 16 residues long, and that's the maximum that you could, in theory, get. So before going and trying all the different combinations, I think it's just good to visualize what could be the answer and then testing it first. So we've been talking obviously about the identical forms of this, and it's really just a matter of writing it out backwards. So I'm going to start at this end and just write 3' here, and then CA, and I'm just going to work my way along this way. So CA, TA, T, T, G, G, and of course when you get halfway you know that it will work, but we'll keep going. C, C, A, T, A, T, G, 5', and these all match up with each other following the normal base pairing rules. And that means that you can have this model, and so the maximum you can get is 16 base pairs. So the answer for this one is C. But I just want to rule out answer D because you can't have 32 base pairs because they would be sort of joined like this. If these are both 16 long, then you'd end up with this region being 32, but of course it's not going to be double-stranded, so the answer can't be D. So the answer for this one is definitely C. So that was answers 90 to 93.